Hello everyone and welcome back to yet another ad hoc video. So today we're going to be talking about this FDA article that was released in December 8th of 2023. And now 7 months ago I already made a video about this, and you're probably wondering, well, what does this have to do with hair loss? Well, this particular article, this press release, deals with CRISPR therapy or CRISPR technology therapy and how two treatments are being used currently right now here in the US to treat debilitating blood diseases. Now, these two diseases or class of diseases would be sickle cell anemia and beta thalassemia. And these two treatments would be Casgevy and Lyfgenia. Now, both of these treatments can be used interchangeably for both sickle cell anemia and beta thalassemia. So how does Casgevy or even something like Lyfgenia actually work? So to show you guys this, I want to go to this graphic over here. And it gives us a step-by-step overview on how these CRISPR treatments work. So the process begins by collecting the patient's own hematopoietic stem cells, and these are blood stem cells. And they typically, they either use a procedure called apheresis, where the blood is drawn from the patient. So they just draw the blood from the patient themselves, and the stem cells are then separated from the blood. Sometimes they may even go into the bone of the patient. Now, in the next step, they kind of have to go into a laboratory kind of setting, right? So now that they've collected the stem cells, these stem cells have to be genetically modified using the CRISPR-Cas9 technology. And the goal of this modification here is to edit the patient's DNA in these cells so that their blood cells will produce the fetal form of hemoglobin instead of the defective adult hemoglobin that causes sickle cell disease and beta thalassemia. So they're essentially removing those genetic abnormalities with CRISPR technology. And here, the fetal hemoglobin can carry oxygen more effectively and prevents the sickling of the red blood cells or the malformed red blood cells that would cause a beta thalassemia. So before these modified cells are returned to the patient has to go through some conditioning, which sometimes would require a sort of high dose chemotherapy that's designed, and it sounds kind of scary, but it's like this sort of high dose radiation not radiation, but chemotherapy that's designed to destroy the patient's existing bone marrow cells. And this process clears the space in the bone marrow for the modified stem cells to kind of engraft into it. Over time, these cells should multiply, and the body should eventually start producing these regular red blood cells that carry fetal hemoglobin instead of those defective hemoglobin responsible for either sickle cell or beta thalassemia. And that's essentially the overview here, right? This is why this thing is pretty exciting, because as soon as you are able to essentially identify a gene that's responsible for a disease, then you can effectively target that gene, and you can kind of remove it, edit. And this is what's exciting about CRISPR therapies, because once you identify a gene and what that gene is responsible for, you can either go about modifying cells by either removing sections of that cell that has that particular gene, right? Or kind of inserting a gene into those cells such that those cells begin producing or encoding the proteins that the gene tells it, right? That's really, really cool. So again, this is a one-time sort of therapy, Casgevy and Lyfgenia, and that's the general breakdown on how they essentially work, right? So just to go into depth to understand why sickle cell anemia is just so horrible, right? And then we'll go into beta thalassemia. But to understand, what is sickle cell anemia? So sickle cell anemia is a genetic blood disorder where you have red blood cells, which are usually round, and they become sickle in shape. I'm going to go to this particular Wikipedia article over here just to go to this image to kind of give you guys the context. So they had obtained this sickle shape, and it's kind of like a crescent moon. And this happens because of a mutation in the gene that makes hemoglobin, and this is a protein that carries oxygen. Now, these sickle-shaped cells can block blood flow and cause pain or even organ damage. So some people who have sickle cell anemia, throughout life, they obtain severe organ damage such that their life expectancy is greatly diminished below the mean of the population. So over here, as you can see in the Wikipedia article, hopefully I can zoom in, and if you guys can't, look at the screen right now, I'll just read it to you. The prognosis for the life expectancy is 40 to 60 years in the developed world. That's a large range. Still, 60 is pretty low for the developed world. But this is primarily because of how debilitating this disease is, right? If you're incurring injuries throughout life, and we all do, right? But people with sickle cell get that to a greater degree, such that when they do produce sickle cells, it gradually damages and, kind of wears out the organs than the average person would experience, right? So, horrible disease. And the thing about sickle cell is it's codominant genetically. So meaning if you inherit one sickle cell gene from a parent, so this would be called the carrier of the sickle cell trait, you'll produce both normal and sickle cells. But if you inherit two sickle cell genes, so one from each parent, you get the full-blown sickle cell disease, and this is worse, way worse than just having the codominant or the single allele trait, right? Because you'll be producing pretty much 24/7 nonstop these sickle cells. Now, there's sort of evolutionary, I guess you can say, understanding of it, where back a long time ago, millions of years ago, it may have been adaptive to have sickle cell anemia, believe it or not. So a lot of people who have this disease are based in Africa or who have African descent, sub-Saharan African descent, right? And the reason for that is due to, again, the evolutionary reason, malaria, right? So in areas where malaria is common, carrying one sickle cell gene trait helps protect against malaria, right? Because this particular pathogen relies on those red blood cells to kind of reproduce themselves. Now, if you have normal red blood cells, these pathogens can easily enter and kind of replicate and reproduce. But if you have a sickle cell, it's not going to happen as frequent, and it can kind of limit the severity of the sickness an individual could possibly have if they are to encounter malaria. So, that's a bit out of the purview of this channel, but I wanted to give you guys the context of this disease, right? Now, going to beta thalassemia, or thalassemia as well. Beta thalassemia is another genetic disorder where the body makes less hemoglobin than normal, leading to an anemia, so a low red blood cell count. And people with one abnormal gene called the thalassemia trait, I'll go over here to this Wikipedia image, they may have mild symptoms of that particular, full-blown beta thalassemia or thalassemia disease, while those with two abnormal genes, being called thalassemia major, they have severe symptoms and need regular blood transfusions. So if you're not producing proper hemoglobin or red blood cells that can properly carry oxygen, you're kind of screwed over. But as you can see in both of these blood diseases, if you have even one trait, you can still express it and it can still debilitate your life, right? So it's pretty severe. And it's great to see that we have these two groundbreaking treatments being used to essentially cure these people. And I want to go to this particular article over here, which really prompted me to make this ad hoc video and just remind people again about how crazy CRISPR therapies are becoming. So this article, titled, quote, "Sickle cell patient cured with CRISPR summits Kilimanjaro," that's a mountain by the way, "setting world record," unquote. And this man, Jimmy Olagari, I think he might be of Nigerian descent due to the last name, he was treated so he had sickle cell disease, right? Full-blown sickle cell disease. He was treated with CRISPR Therapeutics and Vertex Pharmaceuticals Casgevy, this particular CRISPR treatment, and he's been virtually cured. So much so that he is climbing a mountain. Now, for those of you guys who don't understand, as you go up in latitude, so as you go up, let's say climbing a mountain, the air becomes thinner and you have fewer oxygen, right? This is why people typically, like you've seen possibly in the Mount Everest documentaries and such, they have to carry oxygen tank, right? Supplemental oxygen. So if you already have a disease that kind of limits the amount of oxygen you can carry, whether it's thalassemia or sickle cell anemia, then that's kind of an impossible thing to do. If you do that, it can kill you, right? But here he is doing it. So that's a testament to how crazy this particular technology is, to the point where this guy is climbing mountains, right? Literally and figuratively. So this is very, very cool. Now, when it comes to sickle cell anemia, your spleen has a huge function of recycling red blood cells and other immune cells, right? Like white blood cells as well. Now, people with sickle cell anemia and even beta thalassemia, they usually get pain crises and attacks in their spleen, such that you have a buildup of these poorly regulated red blood cells, and it causes the spleen to inflame, and it can possibly damage the spleen. Now, the crazy thing about this is there's the cardio axis, I think that's how you say it over here, and as the spleen becomes damaged, it can also put stress on your heart, and it can cause organ failure to the point where you cause heart failure, and it's just not a good thing, right? So this is why it's so crazy that we have these two treatments virtually, Casgevy and Lyfgenia, being cures, right? And this is why it's crazy that we have this technology, which is already out. I just don't know why the media doesn't talk about it more, right? Obviously, there is a risk to it, as you can see over on the screen. Treatment with Lyfgenia may increase risks of developing blood cancer. And the blood cancer can develop many years after treatment with Lyfgenia. And this blood cancer can be life-threatening and or cause death. So it's not perfect 100%, of course, but I think as we become more refined with CRISPR technology, we can do these things essentially risk-free, right? But also, I want to kind of bring it back in. I want people to understand that, this is even with hair loss treatment or any treatment at all, right? As long as it improves your quality of life, of course there may be risks, right? But you have to make the assessment. I guess in this particular case, the assessment is much more, severe, because the disease that you have would be more severe rather than having hair loss, right? But it's still essentially within the same sort of context. Can you deal with the side effects? And does the potential of side effects that you may get and its severity, is it worth taking the chance in the treatment, right? Because it could be the case that many people, by the way, I don't think it's been documented that, fully documented that people are getting cancers from this, but you have to be monitored, of course, after you get the treatment. But these diseases in and of themselves are going to limit your lifespan, right? So taking the chance of getting these two CRISPR treatments is meaningful because it improves their quality of life. Now, I don't know how I can extend that to using something like finasteride or dutasteride to treat your androgenetic alopecia. But essentially, again, it's the same context, right? Dealing with those side effects, or the potential of getting those side effects, is it worth it? The point where you would actually take the chance to possibly remedy your hair loss to the point where you can even reverse your hair loss? You have to make that assessment on your own. That's an individual assessment. But I'm not done yet talking about these CRISPR therapies, because there's one that I'm very excited about. And this has to do with type 1 diabetes. Now, I have a good friend of the channel. So shout out to that particular friend who watches the videos, who helps a lot. Because they also deal with type 1 diabetes. So, this particular article from diabetes.org, the American Diabetes Association, titled, quote, "Expanded Forward Trial Demonstrates Continued Potential for Stem Cell-Derived Islet Cell Therapy to Eliminate Need for Insulin for People with Type 1 Diabetes," unquote. And this article is from June 21st, 2024, coming from Orlando, Florida. Now, I'm not going to read the whole article because there's one segment of this particular article that I found to be very, very interesting. Now, again, this particular treatment, this stem cell CRISPR treatment called VX880, it says over here, the results demonstrated that VX880 in the phase 1-2 trial for this treatment reduced or eliminated the need for insulin use in patients with type 1 diabetes. Over here, of the 10 participants who completed the day 180 visit, 7 are no longer using exogenous insulin. This is crazy. So there are people out here who are walking around who don't have to use insulin anymore, who are essentially cured of type 1 diabetes. And then it goes on to say, and 2 had approximately 70% reduction in their daily insulin use. That's amazing. So this just goes to show the utility in CRISPR therapies and how effective they're becoming. And again, I haven't heard much of this in the media. Honestly, these articles just come and go, right? They're referenced occasionally, but this is something that should be talked about more, because there's this, doomeristic vibe when it comes to medical science and medical technology, to the point where people think, oh, we're not going to find a cure to cancer. We're not going to find major cures to these major diseases. And it's just going to be a pill that you have to take every day to kind of stave off these illnesses or keep them at bay. No. We're rapidly moving in the era where we're curing people completely with one-time treatments of these debilitating diseases. Of course, these people, have to be monitored over time, but this is very encouraging news. So what the hell does all this have to do with, the majority of the videos on this channel, which have to do with androgenetic alopecia or, any form of hair loss? Well, guys, this is the article that I referenced in my other video back in February 5th of 2024. And essentially, in this particular article, quote, ultrasound-activated particles of CRISPR-Cas9 delivery system for androgenic alopecia therapy, unquote. Essentially, the researchers use CRISPR technology to delete the gene in the derma papilla that's responsible, so in the hair follicle, that's responsible for producing the type 2 5-alpha reductase enzyme. That's amazing, right? And it led to improvements in these mice to the point where they were starting to grow back their hair. So I think there it is. I think we have to put these things into context, right? Of course, it might be overkill for you to one day go in and get a CRISPR therapy injection in your body to the point, so your hair follicles aren't producing the type 2 5-alpha reductase enzyme, right? Maybe that would be overkill. But I think with the more refined technology, right, producing these, in this case, they're using liposomal structures that has this specific treatment, and they're shuttling it into the dermal papilla cell to shut down the production of that type 2 5-alpha reductase enzyme, right? Maybe we can have something like that one day. But of course, we have to make sure it doesn't go systemic, because if it does, well, that could present some problems, perhaps, maybe it won't. Especially when you're done puberty, you probably wouldn't have any sort of issues at all. But at the same time, you can see how this technology could be utilized in people one day, right? You can see where things are progressing to the point where I think we can reasonably have a cure to AGA and other hair loss concerns, possibly within a decade or more. But it's about the feasibility, right? CRISPR therapies, at least as it is right now, as they're currently being produced, as they're currently being used, they're very expensive, right? Like I showed you or, mentioned with Lyfgenia or Casgevy and Lyfgenia. These things are expensive. It's like a $1 million or to $2 million therapy. And it's for more serious illnesses, right? Listen, we all have issues, right? We all think our issues are serious, and they are serious to ourselves, especially when it comes to something like hair loss, right? But I think diseases like sickle cell anemia, beta thalassemia, hell, cancer, kind of rightfully take the spotlight when it comes to treatments. But in general, let's not be mistaken, right? Nothing in scientific development happens within isolation, especially in the medical field, right? Such that, okay, we had an improvement in, this CRISPR therapy for blood disorders. That means we can't apply that technology to androgenic alopecia in the future. That's a faulty way of thinking, right? So we have to understand that whenever we hear a medical science breakthrough, that means a lot for not just that condition where the breakthrough was found, but for other conditions potentially, right? I mean, like, look at all these orphan drugs, for example. All these orphan drugs that were initially used to treat, let's say disease A or illness A, happens to have application for illness B, C, D, E, F, G, etc., ad nauseum. So that's pretty cool. So that was the ad hoc video for today, right? I'm going to try to get Jimmy Olagare on for an interview. If I can't, I can't. I already reached out to him, but he seems to be a very, very busy guy. Just to get, I want to get his perspective on this. How it felt to go through this particular treatment and what it means to him. How his quality of life has improved, right? Because remember, people with sickle cell and beta thalassemia, they get serious pain, right? Their spleen. They get these things called, I'm on the Wikipedia page right now, but they get these things called like pain attacks or, pain crises. And it can really, really mess with their quality of life, right? So the fact that, and let's not leave beta thalassemia out of it, the fact that we are essentially curing these people of these illnesses, allowing them to properly function once again, right? It's amazing. And, well, that's kind of graphic, but I'll get off of that. And, that means the world. So, yeah. Hopefully, we can kind of get a technology like this, and we can be like these mice. We can start growing back hair after our liposomal CRISPR, ultrasound blasted, applications. This is really cool, right? The way they did this. So you have this carrier that has the CRISPR therapy within it, and it goes into the dermal papilla cells, and it reprograms those cells to stop producing type 2 5-alpha reductase enzymes. I think the application of using an ultrasound to essentially blast these particles through the outer the skin layer is actually pretty cool. And in a video that I made before on my channel, I talked about the use of ultrasound therapy sonophoresis and iontophoresis, right? So iontophoresis being the use of electricity, and sonophoresis being the use of vibrations or sound to essentially break the outer layer of the skin, the stratum corneum, I think that's what it's called, in order to deliver a particular topical to, in this case, hair follicles. So yeah, very encouraging, and the future is bright. So yeah, that's it for this ad hoc video. And let me know what you guys think about these particular treatments, and if you think it could be used one day to treat androgenic alopecia or other forms of hair loss. And just as an aside, what are your hopes, right? Do you guys know anyone with these particular conditions like sickle cell anemia, beta thalassemia, or rather other genetic conditions that could potentially be solved with CRISPR technology? So that's pretty much it for this video, and I hope to see you guys on the next one. Peace out.